As my family loves to sail, I always wondered how a sailing boat actually can move without an engine. Therefore, I want to analyze the flow of air around a mainsail. If you look at the sail, you can see a unique curved shape. This shape will be the wall around which the airflow is separated. In the following, I will study two different sail geometries and examine the flow and pressure profile. What results are there to expect? In upward sailing conditions, the boat moves through the velocity difference rather than just by pressure, as it is in downwind sailing conditions. There you can find a big angel between wind and sails. In detail, this principle is similar to an airplane wing. Due to the velocity difference, the lift force acts on the sail. This is known under Bernoulli's principle. To set up this problem, a velocity inlet and pressure outlet are defined. In the middle of the domain, the cross-section of a typical sail is placed. Here, two different profiles are defined. First, the bulgy shape that is typically used for low wind, then a tight shape for high wind. The angle of attack of the wind is 35 degrees, while the sail profile has an angle of either 2.5 degrees or 12.5 degrees. These are the boundary conditions. For the initial condition, the wind velocity of 2.5 meters per second and a zero gauge pressure are defined. When setting up this problem, the following information must be known. To visualize the viscous flow, a turbulence model is needed. The used K-epsilon model adds two additional equations that have to be solved. As the flow separates at the edge of the sail, this can lead to various problems. Therefore, further equations for the near water regions have to be added. Overall, a fine discretization is needed, as a higher grid resolution leads to better solutions of the used Reynolds average Navier-Stokes equation. Here you can see the governing equations. As mentioned, the realizable K-epsilon model is used. These equations, as well as the equations for the non-equilibrium wall function, can be found in the Fluent Handbook. For the realizable K-epsilon model, the eddy viscosity coefficient is dependent on the mean flow and the turbulence parameter. This is better for adverse pressure gradients, which are existent in the simulation. A structural toroidal mesh is used for discretization. Thereby, the side walls have been inflated and the element size is prescribed. To gain a mesh-independent solution, two different mesh sizes were compared. The normal mesh used for all computations has 20 layers of inflation and an element cell length of 0.05 meters. This leads to 62,920 elements. The final mesh has 25 layers of inflation and an element cell length of 0.025 meters. This results in 242,763 elements. To compare the solutions, the wind only has an x-velocity component and two defined lines are compared. As visible in the plot, the results agree quite well, so that the additional computational effort is not necessary. To gain reliable results, the convergence of the lift and drag coefficients, as well as the velocity components, the continuing the K-epsilon equations were monitored. Here, 300 iterations were sufficient to get a steady solution. If we now look at the actual results, the following solution is visible for the low wind profile. For an angle of 12.5 degrees, the flow is following the outline of the sail profile, where a velocity difference on the different side of the sail is present. Overall, the flow is parallel to the sail cross-section. This is the optimal expected solution. When looking at an angle of 2.5 degrees, the flow separation is not as smooth. This leads to an unattached flow that forms the so-called laminar separation bubble due to the turbulent flow, reattached until the trailing edge separation. See the marked spots in the plot. This leads to smaller lift force, which is needed in upwind sailing conditions. Due to the velocity difference, the following pressure magnitudes are found along the sail. Even worse results again from the flat, high wind profile. This is in agreement with the praxis, as a flat sail trim is used for high wind, almost gale. Concluding, the airflow reacts highly sensitive to the cross-section of the sail and the angle of the profile. This is the reason why understanding the aerodynamics of sailing is so important and difficult. In addition, this makes the challenge in sailing as fast as possible.